All right, everyone, welcome back. It is lecture 2 of the hydrogen atom Hamiltonian. We're largely going to get through we'll get through the Hamiltonian part today, and we'll start looking at wave functions maybe at the end of the lecture. And if not, well, for the most part, no matter what, we'll mostly be doing that for the next 2 lectures after this one, even if we don't quite start it today. After that, we're going to talk a little bit about molecular electronic structure, not too much, but a lot of this operator, this eigenvalue, that actually ends really today. There's a lot to talk about though, so we can spend, even though last time we basically pared down the Hamiltonian for the hydrogen atom to the smallest we can possibly get it. There's a lot to look at, so we can look at because it's such a big equation, we can look at the individual pieces, and that helps us understand the results. When you understand the hydrogen atom, you understand all atoms. And again, there's so much to talk about there, it'll occupy 2 full lectures. I'll try to be very careful to point out what you need to know and what you don't. Like what you don't is this, but that you remember where this comes from, right? You don't need to memorize all that. So let's review, and let me, as always, well, I always review, but let me try to point out a very big picture and point out things that are reasonable for you to have digested intellectually, right? Okay, so last time we talked a little bit about how we finished up our discussion of angular momentum, and in 3 dimensions it's a bear. It's in 3 dimensions we have these spherical harmonic wave functions, and the reason we talk about them is that they did show up in the hydrogen atom, but more on that in a minute. We also talked a little bit about that spin type of angular momentum, and you've seen that before, those little arrows that were up and down, and now you know that all fits in with this whole idea of rotational quantum mechanics. So, and that'll come up again when we start talking about things other than hydrogen and molecules, and that'll be next week. Okay, so we talked about that, then we got into the hydrogen atom, and I wrote down the Hamiltonian, which scientifically we try to make things less overwhelming by using symbols. And remember that this is the symbol for the kinetic energy operator, del squared. Squared because, in Cartesian it's dx squared plus dy, double derivative of x, double derivative of y, double derivative of z. So del squared. And we have the Coulomb operator. Remember that E is the charge of an electron. It's negative because I have a proton and an electron, so those charges, Coulomb's law is the charge times the charge. Negative E times positive E, negative E for the electron, positive E for the proton, which is basically the same charge as the electron. So hence minus E squared. 4 pi E naught is just what SI units demand to make the energy comes out in joules. And 1 over the distance between the electron and the proton. Now, unlike the 3D rotational this and that, the rigid rotor, there were no R's. We just assumed R is like a nanometer. That's not the case here. The electron can touch the nucleus, or it can just go away completely if it wants to. So that means that R is now not really a variable. In the rigid rotor, you'd want to call R a variable, which we set to like 1 nanometer. Here, it's an operator. All right, so, all right. Doesn't look too terrible, right? So what do? If you're ever going to solve these types of things with r, theta, and phi, we need to know that the wave function is separable. So 3 functions multiplied. Now, I'm not going to, I try not to bring this up too much, but the theta and phi are usually just expressed as, we're trying to pare down things, simplify things. So we usually give them this little symbol y, which is the spherical harmonic. This is an indication of that you're talking about a spherical harmonic. It's funny, despite the problems we have with conventions and whatnot, we're good about h with a little slash through the top being h bar. And whenever I see a y, lm, that's always a spherical harmonic, so no one has ever taken that for some other purpose. So, okay, again, I try not to ever bring these up because I don't like trying to remember different names for things that already have names. Okay, so then of course we have the wave function multiplied into 3 different functions, and then I take act on the right and divide out by the left. Again, you've seen that many times. And we're looking for a bunch of terms with the different parts each on their own. And you basically see that. Now, I know that there's a theta and a phi here, but we saw that when we were doing the three-dimensional rotational bit. But so again, big picture, I know that we were doing this yesterday, I'm just reviewing still. This is really a lot, no doubt. But I want to point out that 90% of it are sine thetas, and I think sine of theta is not that mind-blowing. And I got a derivative with respect to a variable. Okay, right? Is that bad? It's just that there's a lot of them, and a lot of constants, right? A whole bunch of constants. But constants are just numbers in a calculator. You know, how bad is that? It's kind of bad when you have 20 of them. All right, now I admit that. Okay. Let's see here. Now, also notice that this is mostly the kinetic. Okay, let me start here. Kinetic energy operator, kinetic energy operator, kinetic energy operator, and Coulomb's law comes out right here. So it's really just all the kinetic energy operator. And remember I said a long time ago that quantum mechanics, it's always really complicated because of the kinetic energy operator. That's always the part that makes this hard. And you definitely see that now. Okay, so again, big deal is double derivative of x plus double derivative of y plus double derivative of z. When you're in spherical coordinates, you can't fix r like we did in rotation. Do your separation, do lots of algebra. That's what okay, so that's like what I'm trying to get across. Not for you to memorize this, I don't think you could, I don't think I can. But just to know that we're starting with the Hamiltonian, that's kinetic energy and potential energy. All right, we're doing the separability thing. Now, I hope you can remember this, because this isn't bad at all. And after a ton of algebra and identities, which don't worry about that, you get to this giant result here. So that's the big picture. And as much as this is scary, if you just know where it came from, it's like you understand people without necessarily understanding every body part, right? I mean, do you have to know what your posterior tibial tendon is to ask someone out? You know, of course not. That doesn't even make sense. So I can just look at this in a coarse picture and just understand that it's mostly the kinetic energy operator. It's in spherical coordinates and whatnot. And then we get into some more finer details, which here's all our angles. Again, our angles are all separated out. And if we assume that the spherical harmonics, I didn't use that little symbol Y there, I don't know if you noticed, but if we assume that the spherical harmonics, the 3D rigid rotor is the solution to this part, then what you get is, from the wrong page of my notes, this is, big bracket, right? Minus L times L plus 1. Now remember, L is the quantum number that is, that's part of the solution to the 3D spherical harmonic problem, 3D rigid rotor. There's always a quantum number. Whenever we have these quantum problems, there's always a quantum number that is related to ground state versus excited states. The number always appears in the equation for energy, and so that's L. Okay, this plus that has got to equal 0, and so therefore I know that this whole deal is equal to plus L times L plus 1. Okay, so again, I don't think that any of us are going to remember this whole shebang in every individual term, but I do get that the separability process creates miniature Schrodinger equations. Each one is solved on its own. Now this nightmare, right, is the 3D rigid rotor, and it's been solved by our Laplace, the person in France in 1782, I think. I forgot what the date was, but anyway, a long time ago. And if we accept that that was solved, then this is what you get out here. So now you have this miniature Schrodinger equation, which is certainly a bit smaller, and it's got to be equal to plus L times L plus 1. Again, I'm still just reviewing from last time. Now what you do with that is you set that equal to L times L plus 1, And you do a whole bunch of algebra. I'm not going to repeat, I did this last time, I'm not going to repeat it, but this is the end result. So, and again, look at this, kinetic energy, potential energy equals to, so, you know, I'm seeing just, here's a Hamiltonian, here's a wave function, it's equal to the energy times the wave function, so we're quite used to that. Yeah, it's a little complicated, that's because it's in spherical coordinates and all the other rigmarole you just saw. Let's see, yeah, there's potential energy. There's not much to it. You just have to hope that someone, which someone did in the 1920s, has solved this. When we have the wave functions and we know the energies, and then there's tricks to do with the wave functions to understand why they do what they do, why atoms look the way they look. Maybe there's a turning point, hint there is, that's on the homework. So with the wave functions, we're going to do a bunch of just all the things that we could possibly do with them. Okay, so yeah, I don't think I have too much else other than to start breaking these down into the individual terms, and let's see, and yeah, and then maybe we'll start writing down the wave functions at the end of class. Also remember that this is, I use a word like, if our miniature Schrodinger equations, right, because of separability, gave us miniature Schrodinger equations, and since we knew this one, which is like the subordinate Schrodinger equation, we have this primary Schrodinger equation, which I call it primary because it's the one that has got E in it, because I've got an R squared E. So this radial Schrodinger equation, this miniature Schrodinger equation, is the most important because it happens to take E with it. And again, we see that here. So this is like our primary Schrodinger equation, and it will give us a new quantum number, right? L and M are from the angles. L is the most important one. That feeds down to the real important one, which is the radial, and it will also have a quantum number n. And we talked about how that appeared in the Rietz combination formula, and how that's actually telling you about rows of the periodic table. Okay, now, again, to understand the parts of it, now these are things I could probably ask you on a test, is like, maybe I'd write this whole shebang out and then just say, hey, tell me what this is. You know, what's going on? Okay, well, I hope that you can see that, excuse me, this is kinetic energy. I mean, it has to be because there's the potential energy that makes all of this kinetic energy. It was derived from turning the double derivative of x plus double derivative of y plus double derivative of z. It directly comes from turning that to spherical coordinates. Unbelievably large amounts of algebra, yes, but that is still where it came from. So this is kinetic energy. All right, now I can ask you, does it raise or lower the energy? And I would do that because of that minus sign. And some of you are going to say, well, there's a minus sign there, so therefore it lowers the energy. Okay, how can kinetic energy ever lower energy? How could that ever be true? Because you could not be moving, in which case you're not contributing anything, right? Something not moving has no kinetic energy, therefore it has no contribution to the total. But if it's moving, it's making a positive contribution. So this is not an energy lowering, it is an energy raising. It can only raise the energy. Now, you may be saying, but then why is there a minus sign? Why was there ever a minus sign? Remember when we started on the first day of quantum mechanics, when we looked at how Schrodinger had figured out what the kinetic energy operator was, it was minus h bar squared over 2m double derivative of x. The minus comes about because whenever you take a double derivative of a wave, of a wave function, you always seem to pick up a minus sign. So the minus sign is basically to eat that double derivative, what that's gonna do to you. Okay, so again, hopefully that makes sense. Now we can look at this part here. Yeah, let's look at the next part, then that makes sense. Okay, what is that and what does it do? Okay, so this is kinetic energy still. That's the potential energy, so therefore everything else is kinetic energy. And I can't really play that trick of does it raise or lower energy. I'll do that anyway, maybe I'll put this on a test. I mean, I can go ahead and ask that. Of course it's energy raising for all the reasons I just said. But it has a lot to do, this is the rotational part, right? So this would be the kinetic energy due to rotation. I mean, it looks like a bloody mess. I only know that this is from rotation because it has that L times L plus 1. Now think about an S state. Despite its round nature, a particle is not actually rotating. It has no rotational energy in an S state. The one S state of hydrogen has an L of 0 and therefore is not actually rotating despite the fact that the wave function is round. That's so weird, but true. Now you may recall I explained that by saying it has no nodes. When you have nodes, you pick up energy, you pick up kinetic energy. So P states, D states, those have nodes. S states don't have nodes. S states have no energy. So if I have an L of 0 for an S state, then this is 0. And that's how I know that this is the angular contribution, the rotational kinetic energy contribution. Because an S state would not, this term disappears for an S state, and that's all I need to know. And that kind of makes sense. Okay, so you can really break down the details here. Now, again, so that's L times L plus 1, but what about 1 over R squared? I know you're sick to death of seeing this, right? But what happens when I turn in my arms, right? I spin up, right? So the more compact you... it's kind of fun. So if your radius is closer to the nucleus, you'll have greater kinetic energy, rotational kinetic energy, for the reasons that you just saw, right? And when were we? Is it like middle school when you start learning about these kinds of mechanics? And of course, you always see the ice skater pull her arms in, and it's hard for me to imagine being like fascinated or being surprised by that. But I guess at one point in my life, I must have been like the first time I saw it. And again, I think that was like middle school. Okay, let's look at the last one. And again, this is legit. This is legit potential energy. And I know that because there's Coulomb's law. I got a 1 over 4 pi E naught. Whenever I see a 1 over 4 pi E naught in any equation, I know that it's an electrostatic something something because Coulomb's law has 1 over 4 pi E naught. Now, what's kind of interesting about this is if you think about all the other quantum this and that's we've ever done, once we got past a free wave potential surface was just a flat line. So sometimes I drew a flat line. Got a little bit more interesting when we started doing finite, infinite barrier or finite barrier. Recall that, or harmonic oscillator, i.e. bonds. I always drew the potential energy and then drew like the wave function somehow on top of them to convey some kind of information. So notice for the hydrogen atom, despite all the rigmarole, your potential energy is right here. So I'm tempted to draw the wave functions on top of Coulomb's law like I've done with basically everything else. Now what would that look like? Okay, let's draw potential energy. And at best, there could be no potential energy, no Coulombic interaction, and that would require the electron and the proton to be infinitely far away. Okay, now this is the radial part, so the x-axis is the radius, r. The y-axis is potential energy in joules, which, or maybe we'll do EV or something, I don't know. And what does 1 over r look like in a graph of something versus r? Well, 1 over r versus r, it looks like that. Hopefully I've done, I think I've done that well enough I don't need to use a computer to draw that. What's really nutty, though, is that all the energies are negative. In fact, the potential energy is so negative, the kinetic energy doesn't overcome it to contribute to the total energy. So again, the potential energy is so negative that this thing is not going to match that and go over to yield a positive energy. The energies that we calculate for the hydrogen atom are negative. This is very unusual. You may recall that all the energies for every system that we have looked at till now, the total energy, this part, has always been positive. That's kind of sensible. In this case, the hydrogen energies are all negative. Now, that may be like, well, there's something fundamentally different. No, not really. It's actually, that almost means nothing. It just comes out that way. The reason is because we don't really observe energies, we only observe differences in energies, and differences in energies will always be positive, right? We're always going from a ground state to an excited state when we use spectroscopy. When I put a cuvette in the little ocean optics thing, like in PChem lab, and measure the absorption of your dye, you're seeing light absorbed from the ground state to the excited state. That has to increase the energy, which comes from the photon. Therefore, only differences of energy are anything you ever measure, and you're always seeing that difference is positive. So it doesn't matter that the potential energy and the final energies are negative. And we'll talk a little bit more about that here in a minute. Let's see. Last bit. When it comes to the solutions, you have an n quantum number. I already said that, but now let me tell you a little bit more about it. It goes from 1 to 3, ... L is a little unusual. It starts at 0 for S, 1 for P, 2 for D. It starts at 0. That was kind of a weird one. If you think about it, we didn't see that behavior. We didn't see in L quantum numbers starting with 0 very frequently. And here, we're not seeing that. We're seeing N starts with the number 1. So that's a little bit more normal. Now we also know, let's see here, that this is going to dictate the energy. And it is also related to the, here I'm going to do a little video, it's related to the periodic table. N of 1 is the first row, N of 2 is the, row versus column, right? First row, N of 2 is where the electronic structure of the second row is like important, and on and on and on. So actually what's happening is you get second row elements because you start filling up like 2s and 2p orbitals, and right, 2s, right, that's the n quantum number, 1s, 2s, n is 1, n is 2, that's the n quantum number, often called the principal quantum number showing up. So only when you get heavier elements do those orbitals get filled up, and that's how they conform to the periodic table. We'll talk a little bit more about that in a little bit. Now there's another weird thing is, we have seen one other example of this, and I know this concept's kind of new. I'm kind of used to it, so I feel like saying this because it's so easy, but I know you're seeing it for the first time, which is when we look back at how separated Hamiltonians have, the angle parts here and the radial parts there, or when we were doing 3D rotation, when we did the 3D rigid rotor, we had phi over here and theta over there. We had this division from primary Schrodinger equations and secondary Schrodinger equations. And I've said that a zillion times now. But what was interesting was, again, with the 3D rigid rotor, you saw that we had an L quantum number and an M quantum number, and that they had a dependency on each other. If an L was 0 for an S state, then the M is 0. If L is 1 for a P state, then M can be +1, 0, or -1. That's like Px, Py, Pz. So there is a codependence, okay? Here, we've got our L quantum number, we've got our N quantum number. There's a codependence. One can't be something and the other something independently of each other. There's restrictions, that's what that means. So maybe if you want to remember things, remember that. Okay. Now, N, like I say, that's like the important quantum number. That's going to dictate the energy, which I'll write down in a second. L has restrictions, especially being like the subordinate, the beta Schrodinger, mini Schrodinger equation, once it's divvied up. So I'm not surprised to see that the L quantum number has to conform to the N. And the way that works is L can be 0, just like I mentioned, L can be 0. 1, 2, so it's a whole number, yada, yada, yada. It can go up to n minus 1. Okay. Now, I'll tell you what, let's bring up that periodic table again. Okay, for an atom with a n of 1, that's the very first row. That has hydrogen and helium. Hydrogen and helium have electrons in the 1s state. So notice that L, if n is 1, L can only be 0. That means that you can only have s states. Okay, on the second row, you could have a principal quantum number in n of 2. Now that means you can have an s or a p. N minus 1, n is 2 is 1. So L can be 0 or 1. That means S or P. Now how many atoms do you have? You have 8, right? You have 2s, and you have 2 electrons, and then you've got, sorry, I'm stammering, 3 p's and 2 of those. So you have a total of 8 possible states, right? Px, py, and pz, and you all know that 2 electrons per orbital, so that's why there's 8 entries. If you go to the third row, now you can have 0, 1, or 2 for angular momentum. That's the d block. L of 2 are the d orbitals, and of course you can have 5 of those: dz squared, dxy, dyz. I don't remember the rest, but anyway, there's 5 of them. Okay, so I just want to point out that that also makes sense. And last bit, don't forget that that m is still, just like I mentioned a minute ago, m is still minus L plus 1, to plus L. And again, if I have an n of 2, an L of 1, that's a 2p state, then I have a m of minus 1, 0, and plus 1, and that's where I get px, py, and pz. Now don't let that blow your head off. You know that there's a 1s orbital. On the next row you can have a 2s orbital, you can have a 2p orbital, and there's px and py's and pz's. You know that there are 3s orbitals, 3p orbitals, and 3d orbitals, dx squared, dxy, dyz, and the other 2. So you know that. You're just seeing stipulations of where they come from. They come from this separated Schrodinger equation that have some codependencies on their quantum numbers. And that's why you have like that pattern to the periodic table. That's where that comes from. Okay, so last bit, and then we're going to have to get into some more details. Actually, we're going to, what we're going to do next is we're actually going to solve the, I'm actually going to remove terms from the Schrodinger equation and solve them, and to show you what the final answers look like, the radial wave functions. This is rather complicated, obviously, and so that we can understand what the wave functions look like, I'm actually going to be eliminating terms in a sensible way and leaving us with things that we can solve relatively easily. Okay, anyway, so that's what we're going to do the rest of the class, but let me just give the last detail. I'm just babbling because I have to erase the board here in a second, and I actually really hate doing that. Okay, the energy. Now, we have the wave functions. They were solved in the 1920s. Plug them into the Schrodinger equation, and out come the energies. And here's the result. The energy ends up being, and don't worry about, I'll never show you this again. I'm going to write this out in terms of constants, and then I'm going to put in numbers in the constants. So don't worry too much about these details. I just want you to, you're just used to a mess of constants coming out more and more when it comes to these energies. And here we go. So a bunch of constants. Remember, that's the mass of the electron. E is the Coulomb charge of an electron, like 1.7 to the minus 17 or something. I don't quite remember. Pi squared is pi squared. There's our permeativity of free space, h bar, and here's our principal quantum number. So our principal quantum number is always shows up in the energy once you solve a Schrodinger equation or a miniature Schrodinger equation. And last bit, I want to show you that in EV. This is common. So just don't worry about all these constants. 13.6 EV divided by n squared, the principal quantum number squared. Now you can see why you can't have a principal quantum number of 0, because that would be infinity, which you're not allowed to do. And 13.6 EV, by the way, big number, small number. You may think 13 is a small number, but 13 EV is a just substantially earth-shattering high energy. That for an atom. For an atom to have 13 EV, it would just explode just immediately. That is a tremendous amount of energy for like a molecule to have. I mean, just unthinkably large. Okay. Now, let me just do one last thing before we get into a little bit more of the mathematical stuff. I'm a little bit descriptive right now, which I think you appreciate. Let's see, what do I want to say? Let's say that you have, maybe I'm doing the spectrometer. Okay, we talked about how you can leak hydrogen into the spectrometer. Hydrogen comes in the form of H2, so then you hit it with some lightning, just make an arc, right? Arc of electrons, go through it and blow those hydrogens, those H2s into pieces. Now I've got hydrogen atoms, not for long, but I've got some hydrogen atoms in the spectrometer. And now what I want to do is, I want to shine, it's going to be UV light, I want to shine UV light to make the electron come off the hydrogen. So despite the violence of the preparation of hydrogen atoms, and again I have to do some nutty things to get hydrogen atoms, not H2. I want to cause the electron to, I want to ionize it. I want to get the electron off the atom. How do I do that? Well, I need to use photons, and I need to know the energy of those photons, and again, it's going to be pretty high energy. Now, how would I use this to figure that out? Well, I'll show you, which is, okay, so delta E, so I am going to shine light on this. There's my constant. I'm going to shine light on this to cause the electron to fall off the hydrogen atom. Now, all I got to do is I got to take the final energy minus the initial energy, which is dictated by F. Okay, so I've got final minus initial here. But what does that look like? All right, well, if I'm looking at this thing, this potential energy surface, 1 over R, I'm going to have to get this to a very highly excited state with, remember, N of 1 is the ground state, N of 2, N of 3, those are excited states. If I can drive this to, say, the infinity end state, then that would have to have the electron just completely ripped off the atom. Right now, yeah, that kind of makes sense because then it would have no energy. The energy is all Coulombic. So if I had an N of infinity, then there's no energy, and that means that the electron and the proton are no longer interacting, and that means that they've been pulled apart like all the way to infinity. Okay, that rambling blah 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 is meant to tell you that the final state has an N of infinity. And again, that means that the electron and proton are no longer interacting. That means that the energy is 0. And of course, the initial state will be N of 1, because that's the ground state. Hydrogen will be in the 1s orbital, which we know N is the principal quantum number. That's 1. N of 1 is the ground state. Okay. So what is this? This, of course, is plus. Remember, I was telling you that when you look at this in a way that is meaningful, like how would you? These negative energies don't matter. Only differences in energy matter. And look at that. That's positive. Now, EV in terms of nanometers of light, because when you do UV vis, you're always looking at nanometers. Typically, your UV vis, like in PChem lab, is typically from like 250 to 300 nanometers to around 700 nanometers, which is the near infrared. UV to near infrared. Okay, this is 91 nanometers. So that's some real high energy light. That's extremely high energy light, by the way. If you were to take a sun bath, a tanning salon at 91 nanometers, I even asked some people at Argonne National Lab about this, and they told me, they were like, well, you wouldn't, I said, would you die immediately? And one person said, yeah, you'd die immediately. And another person said, no, you wouldn't die immediately. You die in about 3 months. I was like, well, what does that mean? Well, you'd have cancer everywhere. It's not going to kill you instantly. It takes about 3 months. So 91 nanometers is scary large. All right. Now, last bit is I can plot this. I can plot this on the potential energy surface, and it takes a little bit of head scratching, but plotting this as a function of principal quantum number, it's a little funky how it looks. So I'm going to do that here. This will be the 1s state. Right now, 1 because the principal quantum number is 1, and I'm saying S because L can only be 0, and an L of 0 is S. Okay, so the hydrogen atom ground state is a 1s state. Okay, and this is, I've already lost my spot. This, of course, is at an energy of minus 13.6 eV. I just said that, right? Just minus 13.6 over 1 squared. Okay, the next one is an N of 2. And the hydrogen could be in a 2, so this is N of 2. Hydrogen could be in a 2s or a 2p state. Those are allowed because with an N of 2, L can be 0 or 1. They would be degenerate, right? Because the energy depends on N, not L. Therefore, 2s, 2p, whether px, py, and pz, those are all the same energy, and that energy is 13.6 over 4. That's minus 3.4 eV. Still a pretty big number. That's like, if that was a photon of 3.4 eV energy is still like UV. Okay, N of 3. Now notice that I have to get these closer and closer, and their proximity increases as basically the square, right? So N of 3. So I could have a 3s, a 3p, or a 3d, and those would all be degenerate for the same reasons I just mentioned. And this is minus 1.5. And this would be red light, by the way, or it could be infrared. So that's actually not nearly so much energy. 13.6 is enough to destroy a molecule. 1.5 eV is not that much, really. It's funny how quickly that changes. Okay, now if I was to draw more of these levels, and I won't, they have to get ever increasingly closer and closer and closer, so I can't really draw that, but hopefully you get the idea. And again, now another thing, we don't really need to worry about this, because if you look at the periodic table, N of 1, 2, 3, 4, 5, the periodic table doesn't really have that many rows in it, right? Or am I talking about columns? No, rows. I'm talking about rows. You can't have atoms with very high end states because they just become unstable. That's why the periodic table only has so many rows. I'm not going to worry about going past the n equals 3 state, because I'm going to tell you some things about d orbitals. I'm going to talk about s, p, and I'll tell you about d orbitals, and I'll stop there. F orbitals, we can go to F orbitals, like, we're not talking about plutonium and uranium and Einsteinium and all that. We won't worry about those. It's just more of the same at that point. Okay, so I see I have 15 minutes left. So now we're going to have to get into a little bit more of mathematics. So give me a moment. I'm going to wipe out the board, and we're going to start looking. We're going to keep looking at this, but we're going to look at that in finer detail. So I will be right back in just a moment. Okay, so I'm back. All right, so I won't be able to finish all this in this lecture, which is to decompose this a little bit further to understand what the final wave functions look like, and that will be next class. And let me, I know it's kind of hard to describe, so I'm a little fumbling with my words here. I guess the best I can do is state that what we want to do to understand the Hamiltonian, because that dictates the wave function, so we're going to start trying to understand the Hamiltonian a little bit better, is to think of four limiting regimes. I don't know if that's the right way to express that, but that's what I'm going with. And let's see, we're going to think of the wave functions, the radial wave functions, in terms of L equals 0, which is an S state, and L greater than 0, which are P and D states, and F states, but I said we're not going to talk about F states, that's painful. Okay, those have a lot of fundamental differences, so, and we're going to go over those. Next bit, now this one's kind of easier to understand, are close and are far. Now that means close and far to the nucleus. An R of 0 is where the nucleus is, and an R farther away means the electron is like leaving the atom. So, Now, one of the things that's kind of interesting about the quantum mechanics of the hydrogen atom is it assumes that the electron is a point particle. Now that means it has no volume. It assumes that the nucleus is a point particle that has no volume. It's not really true. Electrons, neutrons, protons, they have volumes. They're really, really small. So it's actually not quite right to treat them this way, but that's what we're going to do. Just heads up on that. So an R of 0 means that the electron has crashed into the nucleus. So we have these 4 areas. So we can think of like 4 regimes that we're going to study. For the first one, let's look at the effect of L of 0 and L greater than 0. So, and I won't worry about so much about being close or far away from the nucleus. Okay, now the important thing here is I've got Coulomb's law. So let me, I stupidly deleted that, so I have to redraw that thing now. Okay, so here's our potential energy. It's only negative, which is weird, but okay, R is still is like the x-axis. Okay, and potential energy looks like this. I'm actually relatively smooth like that with that, so I don't think I need to computer graphics that one. Oh, that line isn't straight. That bothers me. There we go. Okay. Now, this is the potential energy for the Coulomb part. And it also has to be true, it's absolutely true if L is 0, right? Because then that term is gone. We're going to worry about that in a minute. So, we're trying to figure out what L of 0 versus L of not 0 do. So we're just going to look at this and this. Okay. Now, if L is 0, then that's, this Coulomb's law is the only thing that's there, right? That term is gone. So if L is not 0, then what you get is, at far distances, 1 over a big number squared means that this actually isn't going to do much. But when R becomes small, 1 over a small number squared ends up being pretty dominant. And the term is positive while that's negative. Okay, now what that means is that, so it's always going to raise the potential surface. It's always raising it. But it doesn't do a lot until you start getting real close to the nucleus, and then all of a sudden it dominates. There you go. So this is L greater than 0. Now remember, L is 0, 1, 2, 3, 4, right? You can't be 0.5 or something like that. Okay. So that's for L greater than 0. And that means that the potential energy is proportional to minus 1 over R, like you see here, plus L times L plus 1 over R squared. And now that means that when R is small, oh, that bothers me, that R needs to look better. There we go. At large R, this one's dominant, but at small r, that one's dominant, because 1 over a small number squared is a gigantic number, and it will wipe out that one. So that's why it looks the way it does. Okay, now with that, let's see. I should have done this on another board. Let me wipe this out, and I'm going to start manipulating this. And I'm going to do so in ways that don't seem really sensible at first, but you know, whenever I do that, it's because 2 or 3 steps later, all of a sudden everything is like way simple. And again, I don't know how people knew to even start these types of derivations, but maybe they knew the end and worked backward, like reverse engineered it. I've always wondered that, but they're all dead, so I don't know. Okay, so what do I want to do? Here's my instruction set for my algebra, and what I'm going to do is multiply by r. So take this and multiply by r. Again, I know it seems like, well, why? Well, because, okay, so maybe I'll speed up time because this is time consuming. All right, there you go. Okay, notice I did something funky here. So I've multiplied everything by r, and so this 1 over r is now gone. That makes sense. I did something a little strange here. Instead of just making this 1 over r squared 1 over r, I kept it and I put an r in front of the wave function. Now, why did I do that? It's because here I have r times the wave function, r times the wave function, r times the wave function, r times the wave function. I wanted to keep it that way because that makes finding the solution a lot easier. So that's why I did that. Okay, now what? Okay, now we're going to have to start talking about short versus long distances. Okay, so again, my instruction set. At short distances, that of course means r is close to 0. Okay, if r is close to 0, oh god, let me stare at this for a while because I'm going to, okay, so we're going to make that 0. Now, if e times r times the wave function, that r, if r is close to 0, that justifies just that's 0. Okay, let's see, what else can I do? We can also eliminate, we're also going to eliminate this. Is that right? Yeah, we're going to eliminate that for the same reason. I've got, oh no, wait a minute, have I messed this up? Oh, you know, no, I just left an R. I left an R at the bottom, sorry. Anyway, that looks bad, doesn't it? Sorry, I messed that up. Okay, still though, for the same reason, let's see here. I've got a 1 over r squared, and again, 1 over a small number squared is very large. So this is definitely a very large term. And this has no r dependence, and this is dependent on r. So it's reasonable to expect that this is going to really get big compared to this or that term. That's why we're setting those equal to 0. Now, I'm tempted to get rid of this too, but then that leaves literally nothing to do. All right, so that's why I'm doing it. I know that's a little weird. Let's see, now what? Okay, last bit, and then we're done. I see that I'm running out of time. Okay, I'll speed up time here because I'm just writing a bunch of stuff. All right, there we go. So those are just all the simplifications I made. And now if I can simplify it a little bit further, what you get is just some algebra. Those h bars are all going to go away. It's really much nicer. And again, I'm always solving for r sine of r. It's equal to L times L plus 1. There we go. Again, that's just an algebraic simplification. Okay. Now again, I know I'm out of time, so the point of this is that I've now got myself a smaller Schrodinger equation that is for short distances. And what I want to show you is that a solution to this is r to the L. Okay. Now what that means is, and I'll prove that here in 1 second, I know it may go a little over time. The point of all of this exercise is that every wave function for the hydrogen atom, every radial wave function has r to the L in it. And this is kind of an explanation why. It has to do with the angular momentum part. It has to do with preventing the electron from basically gaining too much kinetic energy as it gets close to the nucleus. That's the explanation. So that, energy doesn't go off to infinity. Now, to prevent that, you have an r to the L term in there, which is, again, a solution to this for when you're talking about an electron getting too close to the nucleus. Okay, now, to double check that, let's do the double derivative of r times r to the L, so that's r to the L plus 1. Hopefully your algebra is good enough to do that. Then what have I got? I've got this equal, well, why don't I just do this? This is the derivative with respect to r of L plus 1. R to the L plus 1 minus L is r to the L. And what is this? The derivative of this would just be L times L plus 1. I've taken that L, I've put it up in front, r to the L minus 1. And that's, yeah, that's it. Okay, so that's this part. Okay, let's look at this. L times L plus 1 over r to the L. Well, r to the L over r is r to the L minus 1. Okay, so there you go, that's a match. All right, so I see that I've probably gone over time. Again, the big picture is that we've got this radial Schrodinger equation. We've talked about principal quantum numbers and energies, how the periodic table is laid out. It all makes sense, it's all consistent. And now we're going to start trying to understand the wave functions. I haven't shown them yet. And we want to look for trends. We want to look for trends that explain what happens when the electron gets too close to the nucleus. And what it means is that every wave function has an r to the L in it for all the reasons that we just did. Now, unfortunately, I'm out of time, but next time we're going to start with this, and we're going to, this is the full equation, and then we're going to ask what happens when r is very far from the nucleus. And then I'm going to write down all the radial wave functions, well, just a bunch of them, not all of them, all right? That would literally take forever. I'm going to write a bunch of them, and you'll always see that, you're always going to see that r to the L. R to the L is in every one of them, and the solution at longer r's as well. You're going to see that in every one of them. And then we're going to do even more stuff, and then that's that. We're close to graduation at this point, aren't we? So, okay, with that, I will quit talking, and I will see you all next time.